Hi guys, sorry, we're a couple of minutes late. Wednesdays, I have to switch classrooms. All right, so today we're gonna talk about, we'll start a new lecture on machine translation. Yeah, so we're starting now, if you could wrap up. Thank you. So in terms of logistics, everything else is the same as last week. The only new thing is the A2 tutorials. Please put this in your calendar. We have 2 tutorials, and the third tutorial on March 10th will be over Zoom with the head TAs. And I just added this, thing about code last night. So it's a request that once you're done with your assignment, please do not post your solutions on public repositories. Among other things like copyrights and whatnot, I think it really hampers the prospect for future students to learn. And the other side of it is that there are some public repos. I would suggest that please do not use them because we're also aware of it, and you may run into subtle problems that might. The thing is that we're not here to police you. We're just here to make sure that you succeed, and please. Please don't use those public repositories, and the assignment is different this year anyway. All right, thank you. So let's start. The 2 assignment head TAs are Frank and Gavin, and please use this email address for all correspondence related to A2. So this lecture is divided into 3 parts. Today we'll look into the classical or statistical machine translation. And the next 2 lectures will look into neural machine translation, sequence-to-sequence encoder-decoder architectures, attention mechanisms, transformers, and the 3rd lecture will be on how we can evaluate or train this machine translation models. So it's good to start with the story of the Rosetta Stone for this lecture on machine translation, because this story captures the intuition of modern-day machine translation. So the word Rosetta is the Italian word for Rashid, the town of Rashid near Egypt, where the stone was first discovered. And this stone dates back to the Macedonian era, when the Greek era, when the Macedonians conquered Egypt, and this stone had the same decree inscribed in 3 different languages. It was rediscovered by the French soldiers during the French Revolutionary Wars, and when it was rediscovered, the first two languages in ancient Egyptian languages were already lost in the ravages of time, so there's no way to decipher the first 2 languages. But this provided an opportunity because there was 3 parallel texts in 3 different languages with the same meaning. And at the time of rediscovery, only ancient Greek was understood. So what followed is a period of research to decipher these forgotten Egyptian languages. And there were many different researchers, but this person, Jean-François Champollion, will be our composite character. So he noticed that in Egyptian languages, the circle symbols, which are called cartouches, appeared roughly in the same position as the word Ptolemy in Greek. Ptolemy was the ruling king at the time of the inscription. And then he gathered some more. So he hypothesized that this cartouche outlines like royal names. So to test his hypothesis, he gathered the cartouche of other famous Ptolemaic rulers, for example, Cleopatra. And then he aligned them up, and from there, by alignment of those cartouches, he sort of started deciphering what each of the symbols meant. And so for example, for the cartouche of Ptolemy and Cleopatra, some of the symbols, so he knew how the names are pronounced, and he lined up the names and then proceeded to see that maybe this rectangular symbol is pronounced like P, and so on. Yeah. So this deciphering of the Rosetta Stone was the first demonstrated value of working from parallel text to decipher an unknown language. And without this aligning or with this approach, or it wouldn't be possible to know like unknown words or Egyptian hieroglyphs to known words Greek. And with that sort of motivation, we start our today's lecture on statistical machine translation. Yeah, so I think today's lecture, as I said, that today we'll be talking about classical or statistical methods, which we no longer use in practice today, but it's very important for you to know the precursor so that you can have a better understanding, deeper understanding of more modern models. And some of the concepts like alignment is still valid and will be valid no matter what, like how much we advance in our state-of-the-art models. So by definition, machine translation is the system where we take in utterances or sentences in one language and transform them to another. The easiest way to do this is to use a bilingual dictionary. So where you pick word by word and do a direct translation and to do the translation of the entire word. But as you can already imagine that such direct translation would not result in a very efficient machine translation model because of the language caveats that you have seen in first lectures. First, we have the structural differences between different languages or typological differences that makes such direct mapping almost impossible. So for example, you can have like polysynthetic language like UPIC where an entire sentence can be represented by one word. On the other side of the spectrum, you can have Cantonese where each word is indivisible. And similarly, you have languages, fusion languages like Russian, where you can have many different meanings conflated into one morpheme. And you can have agglutinative languages like Turkish, where each morpheme can represent a different feature. What I mean by that is that you can have a prefix that means gender. You can have another prefix that signifies the plurality or singularity of that word. What I mean by morpheme is the smallest lexical item in a language. So, for example, if you take the word unbreakable, it has three morphemes. Un signifies like negates. Breakable, break is the root morpheme, and then you have able, which signifies the ability to do something. So, yeah. And we also have the syntactic caveats, like in English, we're used to subject, verb. The order of sentence is subject, verb, and object. Like he listens to music, where he, the subject, listens is a verb, and music is the object that is listening to. But that may not hold across different languages. For example, in Japanese, this is a subject, object, verb, where the object comes before the verb. And verb, subject, object in Arabic, for example. So we also have this other, another example of that is verb versus like satellite framed words. For example, in English, the bottle floated out. The direction of the verb is coming after the verb. But if you translate that into Spanish, la botella salió flotando, where the direction of travel is coming before the action of floating away. So this kind of problems. And we also have not only structural differences, we also have ambiguity, right? So we have ambiguity just for English. And then if you think about a translation task, that you'll have ambiguities in the target or source language, both languages. So we're also trying to translate across the ambiguities of the source and target language. So for example, in paw means, paw in English translates to pâté in French, which may translate to foot, or which may also mean pied, which is strips of color, I think. So doing such like direct translation is very difficult. And then you have more semantic ambiguities, right? So you can have the same structure order, but you have different, same token sequence, but different structure. So Rick hit the Morty with the stick, and Rick hit the Morty with the stick. Well, when I say it out, it just sounds like I'm repeating the same sentence, but I guess a better example is that, like, we saw a policeman with the binoculars, with a binocular. So in this case, like, what is the meaning? Do we mean that we are observing a policeman that has a binocular, or we are using a binocular to observe a policeman? So things like that. And also semantic structures like "I'll pick you up" can mean two different sentences in French. Okay, I'm gonna skip pronouncing the French sentences, so I don't want to butcher it. But it can mean two different things, maybe a literal sense of lifting someone off the ground, or it could mean something in a romantic sense, maybe. So yeah, you get the point. We also have pragmatics. So different contexts, different interpretations. It could be a question in English, do you have the time? But we are not expecting the answer yes or no in that case. We are expecting the time. So in poetry, you will have a more flowery language, and versus a technical report, which could be very objective and very structured. All right, so this is an image of a babblefish. Can I see a show of hands? How many of you get the reference of a babblefish, or do you know what a babblefish is? Okay, just one. That's interesting. Okay, so maybe the reference, it's a little bit too old, but it's a reference to the book or the movie Hitchhiker's Guide to Galaxy, where you have babblefish that you can put in your ears, and that basically acts as a universal translator across galaxies. So, the pursuit for babblefish in real life, it's been a difficult hard problem. And if you're interested in AI history, it is an interesting read that before the advent of the neural machine translation, for a very long period, this has been a very difficult problem, even though a lot of money was sunken into it for research and in the applied field. And success wasn't observed until there was a radical change in perspective to look at the problem. And that is the noisy channel idea that was introduced, or that was thanks to the works of the great Claude Shannon. And here, this famous comment by Warren Weaver in 1947, who was influenced by the earlier works of Claude Shannon, is very illustrative. So he combined machine translation with communication and cryptography. So he said that, when I see something in Russian, it's actually not Russian, it's actually something in English, but we just need to decode it right. It's just been corrupted by some noisy channel. And at the bottom, you see the noisy channel depiction by Claude Shannon. So it is influenced by signal processing, the domain of signal processing, that when a transmitter is transmitting a signal to someone and the receiver is never getting the exact same signal, it is some sort of distorted form of the original signal that was transmitted. And the reason of distortion is because it passes through a noisy channel, and then it distorts the signal. And the task is to basically decode the original signal based on some distribution of the noisy channel, like how does the noisy channel distort the original signal. So yeah. So how can we use this noisy channel model for our task, that is machine translation? So we'll use, in this slide, or in this course in general, we'll be using French as, unless otherwise mentioned, French as the French is the observed language, and we're trying to get the translation in English. So you observe a French sentence F, and you want to convert it to the best corresponding English sentence, E star. And probabilistically, it's basically getting an argmax of probability of E given our observation F. We can modify this using Bayes' rule, and that becomes probability of F given E times probability of E over probability of F. Here, the PF does not affect the argmax operator, so you can ignore it. So we are essentially interested in the numerator over here, and this is where we're going to focus our attention on. Okay. All right, so this is another depiction with our setup of the noisy channel. So we're observing F, and we're trying to decode it to our best possible highest probability, or E star, argmax of the equation that we saw in the previous slide. And the two important components that we need, one is the translation model, which is essentially probability of F given E. And the second is our language model, which is the probability distribution of the, our target language or the source, like the original distribution of probability of English, or the language model of English. So the language model is something that we already know and you have seen. So you know how to calculate the probability of PE, how to do language modeling. So the unigram distribution, bigram distribution, etc. So we know that. So the way we're going to proceed in this lecture is that we'll drill down over this guy, this translation model. And we'll try to find out how we can learn this, what we need for that. And so for example, like we'll show that you can use parallel corpus like we saw in Rosetta Stone. And if you have parallel context, but how do you align those? We need some kind of alignment between them. So how do we learn this alignment? And so let's go through in detail. Okay, so we have seen this is what we are after, and the language model could be any n-gram model that encodes. Basically, the language model is giving us the word order, right? So if you have the language model for English, you actually have encoded the knowledge that how words are ordered in English. And F given E is a word, or it could be phrase level translation model that encodes knowledge on an unordered basis. So French given English is just giving us sort of like word to word translation, word level translation, right? So if you have the way we looked at it as dictionary, right? If it's a cat, what is the French word, and so on. So now what I want to convey is that we need both of these in order to get a translation that is both correct, and there's naturalness to it. So if we just use, let's say, only the translation model, in this slide, we're using Spanish as a proxy for French. But if you translate the word "que hambre tengo yo" in Spanish to English using just the translation model, Spanish given English, then the argmax will tell us that this is our best translation using only the translation model. But as an English speaker, yeah.
So I want to ask a question about the previous slide.
Okay.
So like in the language model, the E can be a sentence or a document. So we can model the probability of a sentence or document by n-gram.
Sure. Yes.
But for the conditional probability of F given E, the E and F are all words or phrases.
Yeah, it could be words or phrases. So as whatever granularity you're working on, it's going to be consistent, right? So if you say your P is the word order, then FE will be word given word, right? So yeah, it has to be consistent granularity. In this case, it's word level, like what we're describing, what I'm talking about right now. This is word level, but it could be phrase level.
Because it's word or phrase level, so it's unordered, right? Because it's ignorant of the.
Yeah, so that's what we're trying to show, that order matters. Yeah, so so basically a good question or a remark is something that allows you to segue to the next slide. So thank you. Yeah, so if we just use, let's say, only the translation model, then as a speaker of English, we know that this is not right. I think "I'm so hungry" is the right translation. So we need the English language model to incorporate the knowledge of correct word order, like he was mentioning. So once we incorporate PE, or our language model probability, then we see that we're getting the correct output, "I'm so hungry," which is a better English translation than "have I that hunger." Intuitively, if you know of the base rate fallacy, so this is a sort of similar thing, right? So if I tell you that, you have a probability of dying, if you have the probability of you dying from Ebola is 99%, that's not going to really scare you, because you know that even though that's maybe the case, but the probability of you getting Ebola in the first place may be 0.0001 if you're in Canada and you're living in Toronto, so it doesn't really matter. So it's similarly like it's sort of the intuitively similar that you're incorporating the language word order in order to get the final probability. Okay, so now that we know that what we need is a translation model and a language model we know how to get. So how do we learn this translation model, probability of F given E? The solution is something that was applied a century ago. We collect data, parallel corpus of text. And for a long time, the Canadian Hansard data set was a very a dominant or very prominent data set because everything that's said in a Canadian parliament is transcribed into the two languages of Canada. So you already know that like every session has a Canadian English document and a French document. And at a high level, you know that this is exactly the same thing as this said. Now what we're gonna do, what we're gonna look into now in the next slides is that we start with this document that we know that at a high level they're equal. Then how do we align at a granular level? How do we align sentences between those documents and use that for translation? Okay, so this slide just shows the relative pace at which data sets have grown over the years. And you see that we paused in 2010, and that is intentional because if we were to include 2023 over here, then you wouldn't see like the difference is so high that you wouldn't see the relative difference for this period of time. Yeah, and the Linguistic Data Consortium is one of the main curators of NLP data sets. Feel free to go to their website and you'll see lots of available data sets that are pertinent to NLP downstream tasks. Okay, so as I was saying that you have documents that mean they're exactly the same, and then but how do we within that document you can align the components at a different granularity level. You can align them word by word. You can align them at sentence level. You can align them at phrase level, etc. Right? And in statistical machine translation, these alignments are very explicit and heuristic. So one block of text entirely is responsible for a translated block. So what we need to proceed is some kind of alignment between the documents. And we can represent alignment by introducing a random variable A, and as long as we sum it out, so basically we're saying that probability of French given English is equal to probability of French given some alignment, joint probability of French and alignment given E over all possible alignments, okay? And then we're making a simplifying assumption that the way this alignment is organized is it's a set of pairs of set. So each pair is first a French text, whether word or sentence doesn't matter, French text, and its corresponding aligned English text. And you have whole batch of it, like set of this pair sets. And we make the assumption that, yeah.
So the index is the location of the word or sentence in the context, like in the what?
Index, which index?
The index, like.
Oh, it's the index of the tuples here in this case. So actually, let me whiteboard this. Okay, this is good. So you have rows of data, and we're going to pick a particular row I. And I'm saying that this is a pair of French and English. So this is something like you have a tuple, French, A, I, 1. So this here, and then you have English, A, I just signifies the bid. So this row is actually called a bid. A bid is one bid is a pair of French and English text, okay? So this is bid I, and this is the index. So here, this actually, okay, so this index over here, one signifies French and two signifies English. So it's the relative index of the tuple, like it's one index. So it's not zero index, it's one index. Does that make sense? One is French, two is English, okay? So I is whichever bid you're working. So you can have another bid over here. That's everything is the same, just replace I with J. So that should be pretty obvious, right? So yeah, so this is like the structure of A. And what we're saying over here, the last thing, so it's missing one decomposition because it's so rudimentary. Probability of the joint probability of F and A given E decomposes into probability of A given E times probability of F given A and E, right? So so we have, using chain rule, we have this joint probability of French and our random variable A given E, and we're decomposing this using chain rule. So we're introducing a variable A for alignment, probability of joint probability. So probability of A, E times probability of F given A, E. Right? That sounds right? Yeah. So it's this guy is not shown in the slide. Now, we're making that simplifying assumption that each of these beads, like bead I and bead J, they're conditionally independent, okay? So I can have like whatever word order, or this only matters within this bead, and they're not, like this will not reappear anywhere else. So we can have French, a French sentence like, let's say, we have English sentence, or let's use French sentence, F1 and E1, they're aligned, okay? So in bid I, you can have something like F1 and E1, okay? And you can have another alignment, F6, maybe E7, E8, okay? So this one French sentence, the sixth French sentence corresponds to E7 and E8, English sentences 7 and 8. And you'd have another bid that would say F, A, J, and this would be like basically F6. I mean, there's another subscript over here. I'm just going to use F6, okay? F6 corresponds to E7, E8. Okay, so the conditional independence is saying that F1 and E1, they are conditionally independent. They don't, anything in here doesn't bother them. If with this, sorry, I may be over-explaining. With this conditional independence, then we can decompose this guy over here into the product probabilities of the beads. Okay, French F given E, because this goes, like we're saying they're conditionally independent given our alignment. Given our alignment, so we can just do if it's a conditional independence, then we just do a product. And that gives us that equation. Is that crystal clear? Yeah.
I just have a couple of questions. So A refers to like the partitioning we take. It could be either word for word or it could be sentence by sentence, for example.
A as the random variable is a set of pairs of set, which I just showed. Within that set, you have pairs of like tuples. And tuple in the first place is a French sentence, and tuple in the second place is an English sentence. They are aligned.
How can you interpret the probability of A given E? So you have an English sentence. How can you derive this?
We are summing it out, right? So we're like, yeah, it could be, doesn't matter. Any probability that you can have like, 1,001 alignments, possible alignments. We're going to take each alignment and we're taking a summing it out. So that's why we have this summation symbol here. Yeah.
Is the A, there is a knowledge, then
So that's, yeah, so A is something that we don't know yet. We have to learn it. But this is, I'm just, like, this is the mathematical, like, if had we known A, so this would be how we could get P, our translation model, probability of F given E. Okay, so we'll look into how we can learn A. But at this point, I'm just describing that we're like, there's an alignment A, and this is how we can get our probability of F given E. Okay?
so A is like a graph representing the edges. Is that
A is just a set of pairs of sets. So this is exactly, like, it could be, I mean, whatever, however you want to represent it. This is the data inside. Okay? Yes.
I just have a question about, if we just assume that we separate our text into just word by word instead of like sentence by sentence.
Sure.
In this case, on the right side of the probability, we can just do dictionary lookup of each English word and each French word. And
Sure.
we'll have a probability of near 1 almost every time.
Yeah.
So wouldn't that maximize the whole thing, even though like it costs?
So we talked about this. So if we do a direct translation like that, like, yeah, you can have a dictionary, but that's not going to give you fidelity or naturalness. That does not allow us to circumvent the quirks of different languages. And that is the reason we're constructing our beats at a sentence level granularity. And I think, so for this lecture, like, consider when we talk about a beat, it's sentence and sentence, okay?
So in this case, if we choose A to be word by word, we'll have a high value there.
Yeah, so but we established that word order matters across language. So if we do it at a word level granularity, so then we cannot capture the word order, importance of word order. And that's why a sentence captures word order. So that's why we're doing that in a sentence level granularity. We're not doing it at a word level granularity.
So in this case, P of A given E should be a very low value because we don't want to.
Sure, it can be whatever, but we're choosing not to do it because it doesn't give us the information about word order. Does that make sense? Okay. Any more questions on this? Okay. All right, so as we're saying that, we'll go with the running example of Canadian Hansard, and you have, and this slide shows that the alignment can be off, and it can even go across spans of sentences, and that's why this basically says that why do we need to do the alignment? Although we know the mathematical equation for it, but we don't know the alignment, so let's take a look at how some of the ways we can actually learn the alignment. Okay, so next few slides, let's go with this running example that we have two English sentences, E1 and E2. He was happy and he had bacon. And the corresponding French translation is in one sentence, which I will not attempt to read out and butcher it. So this is over here, F1, okay? And then, and on the right-hand side over here, these are like this lines are the beat separation, okay? So which this just means if you look at the beat representation, like E and E2 corresponds to F1, and E3 correspond to F2, and so on. So given what I just described, just try to think in your head that how would that look in our beat representation, or how would our A look like given this kind of alignment. So this would look like this on the right-hand side in yellow. So 1 and 1, 2 means that French sentence 1 corresponds to English sentence 1 and 2. French sentence 2 corresponds to English sentence 3, and so on. And for example, take a look at A4. French sentences 4 and 5, like this bit over here, corresponds to English sentence 5. Any questions? Okay. All right, so so now we're trying to find the sentence level alignment, and the goal is to find the, now we'll try to find the alignment A. And we'll talk about two broad classes of methods that how we can do this alignments. One is using sentence length, and the other one is using lexical matches or cognates, okay? So the initial alignment methods relied on just the sentence length, and it is a very simple yet effective method where you can think that if you say that each character in one language translates into a random variable times the number of characters. So if you think about it in a character level, then you can say that at a high level, the number of characters in French will be equal to the number of characters in French, or will be in proportion to some constant, and this constant could be learned or guessed. So, for example, we know, like just by looking at the corpus, that French to English ratio is something around 1.06, which signifies that LE and LF usually are close or almost equal. And we define a cost function using LE and LF, and we define a prior fixed cost Cij for aligning I English sentences to J French sentences. Okay, so with this definition, then we define a cost function, and the total cost of alignment is the sum of alignment cost of each of the beads. Then we can, if we have a cost function like this, then we can draw these lines by finding a distribution with minimal cost, and we can find distribution sentence level breakup or sentence alignment shown on the left-hand side. The second kind of sentence alignment is by cognates, which cognates are words that have same etymological origin. For example, the English word pork that we use today has an etymological origin in the Norman word pork. Similar, so the intuition of cognates is that words that have same etymological origin will have similar spellings. For example, zombie in English, the red words are in English and the blue words are in French. So they convey the same meaning and they have spellings that are not identical, but they're similar. And there are always exceptions. And the intuition of cognates is that even if we don't know what the target language or source language says, but we can look at those cognates and decipher the relative position, or the cognates act as anchors in source and target sentences. And the method that Gale used was, he used something called ngraph, which is the same as ngrams, but computed at the character level. So ngraph is basically like four characters or 4 letters. And he tracks all words that have identical 4 letters, and that's how he anchors, and he calls each quadrigraph as a cognate. So the way this is done is something called a dot plot. And the idea is this, that you take the source text and the target text, and you concatenate them on each of the x-axes. And the point of origin is 0, 0. Why, we won't get into that. But once you do that, then you just basically go through the x-axis, and these are like word tokens. And whenever you find a word, let's say zombie, whenever you find a word on the x-axis that has a corresponding word on the y-axis, you simply draw a dot. You simply draw a dot. Now you can see the dark quadrants on the top left and the bottom right. They're they're almost one-to-one correspondence because they're the same, source, and target. What we're interested in is the lighter quadrants on the bottom left and on the top right, which is basically finds the anchor points between the source and target language. And once we have plotted this, we try to find a short path near the bilingual diagonals. And the way it does the alignment is that each path is considered to represent a match between the languages. So, for example, let's say here, if you take this, the Piet French sentence is aligned to the Cuet English sentence. So try to think of how you would represent this in your sets of beads. So for example, in your A now, you'd have a bead. Let's say this is ith row, and then you have something like F, A, I. I'll just index or. So let's use FP and EQ, okay? So this would be like our alignment, right? So from this dot plot, we can actually create A like the one that we have seen. And yeah, so this is the method. Now, just to mention that we can have alignments in other granularities. It doesn't have to be sentence level, as some of the questions were asking. Like it could be pairs of, documents or sets of words as well. But we talked about why, or in this lecture, we're maintaining that our beads are at the sentence level. Now, if we wanted to do a word level alignment, then how could we do that? So if we wanted to do word alignment models, in that case, we'd have to make a simplifying assumption that every word in French or the source language always gets a mapping in the target language, or there's always an English word for a French word, and it doesn't have to be like vice versa. So if we look at the bottom example, you'll see that the top is the source language, and each of the columns have one English word, at least one English word, one English word, and it's not the case vice versa. So for example, like slap, so this corresponds to 3 French words, but so essentially, like this mapping is from source language to target language. So and if we can do this, then we can train a word alignment model using a method called expectation maximization, which we'll cover in HMM. I'm not going to get into the details of that. There were simpler models where they said that A was like uniform prior, and they basically discarded it, and they just went about calculating this probability of beads. And this, how do you calculate this product of like, Fi given the beads, is that at a word level, you can just count the number of times that French word has appeared with this English words or English word, and then divide it by the number of times the English word appears in the total corpus. This is something that you have already seen in language modeling. So there are several problems with this word alignment model, and the main one is that it's not like the target is not aligned. It's not vice versa for English. So let's say if we wanted to translate from English to French, then we wouldn't have the that one-to-one mapping. In this case, for example, the word slap, this Dio and Una wouldn't have anything to map to. So the solution to that was phrase-based translation, which uses the word alignment model, but tries to align phrases instead of words. And basically, the main idea of phrase-level translation is that now you consider the beads as non-empty contiguous spans of words that partitions perfectly. We call each span as an indivisible phrase, so which is denoted by the Fi bar and Ei bar over here, and assumes that phrases are sequential in the target language. With those assumptions, we again go back to what we're after, like joint probability distribution of F and A given E, and that probability is given by this expression over here. D is just a distortion metric, so think of it as a penalty if the phrases don't align properly. So what it means is that the penalty is lowest when the subsequent French phrase starts right after the end of the previous French phrase. So they're contiguous. If they're perfectly contiguous, there's no penalty. If they're not, then there's a distortion penalty. And phi is something, basically, phi is just the relative measures, relative count measures of the phrases that we can calculate from the corpus. Similarly, the way we calculate it for word. So essentially, in this case, what we do is that we count the number of times the phrase F appears with the phrase E, and then divided by the number of times that phrase in English is seen anywhere in the corpus. And the way we count this is using a heuristic measure. We count the pair Fe only if the phrases are consistent. And what I mean by consistent is best elucidated by this example over here. At the bottom, we have the word alignment model that we calculated before. So for example, if we take this phrase Maria no and Maria did not, And the idea is that each of them corresponds to the span. We take the span and we make sure that, in each of their span, there's no other words. So essentially, we look at the remaining rows and the remaining columns of the span, and there is no other correspondence to the phrase words. So this is a valid phrase, so we count that as a valid pair and use it in our calculation. However, let's say we look at the Greenwich and La Bourge Verde. So this, you can see that their span, this is not a consistent phrase, so we don't count it because there's a, the corresponds to A, which is not in the span of the source phrase. So basically, we don't count this. So that's the idea of like how we can calculate the pair FE and then the phi and then basically the total probability using phrases. Yeah, so then if we, how do we, once we have this, alignment model, whether it's by words or phrases, in this case using phrase, we are now equipped to basically go on and decode and get our the translation, like E-star that we're looking after. There are some caveats, computational caveats. So, for example, we sum out the alignment model. There can be infinite, there can be many different combinations. So that summation is not feasible. And in order to circumvent that, we use a heuristic approach called beam search to pick the best sort of alignment. And I don't want to get into, we'll get into beam search in very detail in the third session of this lecture. So I'll defer it to that. But yeah, except for that, I think that is all for the statistical machine translation part of this lecture. And then next class, we'll start with NMT. All right, thank you.